Chapter 6 about the electrochemical impedance spectroscopy, shortly EIS. At the very first time, I will introduce the meaning of impedance with alternating stimuli, and then we will go to the equivalent circuit models to represent the electrochemical processes. How to model and quantify electrochemical reactions. The primary properties that can be controlled and observed in the electrochemical processes are current and potential. Of course, you are very accustomed to current and potential in the electrochemical processes. The circuit elements used in electric engineering can describe the relationships between current and potentials. So I'd like to use those circuit elements to represent our electrochemical systems. Three basic circuit elements have been used in electric engineering. The first one is resistance, second one is capacitance, and third one is inductance, or resistor, capacitor, and inductor. Let me try to explain about each circuit element, R, C, L. Let me start with the resistance. The resistance is based on the Ohm's law, as you know. So V is equal to IR. What does it mean? Potential is just proportional to the current, and the proportionality constant is resistance. We don't need to use any time function of potential and current. That is to say, you don't need to vary the function of potential and current with time. So let me say this is the steady state equation for relating the potential and current. So here is a single resistor, and the both ends of resistor is connected to the potential state. Then let me allow the electrons flow from the left to the right. In that case, if you have 1 ohm for the resistor, then and then let me apply potential into both ends of the resistor. 1 volt. I'm applying 1 volt to this resistor, and then let me check the current. So if you have 1 ohm resistor there, and then current is flowing at 1.0 ampere, it means every 1 second 1 coulomb is passing through the resistor. Then if you have 2 ohms there, the current is going down to the half values of the original one, something like that. In this case, I didn't change the potential with time. At steady state situations, we have some values about the current or potential. Then let's go to the second equations. Okay, in the first equations, I have said potential is just proportional to the current. And in the second and third equations, I'll try to differentiate the potential or sometimes current. In the second equations, here is the first derivative of potential with respect to time, and dV dt is proportional to the current. Then the proportionality constant is defined as the capacitance. So actually this equation is converted to the Q is equal to CV, because after integrating both both sides of these equations with respect to time, then current is going to Q and dV dt is going to V. So Q is equal to CV, which is the definition of capacitance you have learned in the university physics. This equation comes from this relationship where current is just proportional to the first derivative of potential with respect to time. Only when your potential is varying with time, then you could obtain the current. That is the capacitance equation, and let me say this equation is potential dynamic equations because you are changing the potential with time. It is not the steady state. At the steady state, you cannot obtain the current because dV dt is going to 0, so current is 0. Okay, here is the capacitor. As you know, a single capacitor has two metal plates as electrodes, and here those two electrodes is connected to a potentiostat, and I'm applying some potential at 1 volt. What happens? At the steady state, I mean enough time after I have applied a potential into the capacitor, then current is not flowing. It means current is 0, because we need to have the potential change with time. At the steady state, applying potential, then current is 0. Look at the shape of the symbol for capacitor. We have just two plates. Between them, nothing there. Then at the steady state, everything is on their own sides, and then of course anything or any charge carriers is not moving between the electrodes, so current is 0. However, let me change the potential from 1 volt between the both ends of capacitor to 2 volt during 1 second. It means I have changed the potential at 1 volt per second. Then what happens? Some charge carriers are moving during or while your potential is changing with time. If you have 1 farad for our system, then you could obtain 1 ampere, like the delta is equal to 1 volt going to the 2 volt, so delta V is 1 volt per 1 second with 1 farad is going to 1 ampere. So only when we are moving the potential with time, then you could obtain some current. Current is proportional to dV dt instead of just voltage. That is the capacitance or capacitor equation. Potential dynamic situation is required for getting the current. That is the second equation. And let's go to the third one. Can you expect what kind of relationship between potential and current will be presented in the third equation? Maybe yes, because at the very first equation I have said potential is just proportional to current. In the second equation, current is proportional to the first derivative of potential with respect to time. How about the third? It's time to differentiate the current instead of voltage. So voltage is proportional to the first derivative of current with respect to time, and the proportionality constant is defined as inductance. And I'd like to say this equation as galvanodynamic equations instead of steady state, instead of potential dynamic equations. It means only when you change your current with time, then you could develop some potential. If you are on a constant current for some time period, then voltage is not developed. Here is the coil of copper wire. That is the inductor, you know. Then I am applying a current at 1 ampere through the copper coils for a specific time period. In that case, at the steady state, voltage is not developed between the ends of copper coil. Of course, this is just electric conductor, and it is natural that the potential is not developed along the copper wire. It is just coil. Basically it is the copper conductor. However, let me change the current from 1 ampere to 2 ampere during 1 second. It means the current scan rate is 1 ampere per second for dIdt. And also let me assume that the inductance for this copper wire coil is 1 Henry. Then 1 volt is developed only when you are moving the current at the rate of 1 ampere per second. That is the inductor. So we have 3 different potential current relationship, which is represented by the circuit elements having resistance R, capacitance C, and inductance L. So we'll use those circuit elements to represent our electrochemical systems. Okay, so what resists or impedes electron flows in electrochemical processes? As you know, resistor is the element to resist or impede or hinder electron flow. Those 3 words have exactly the same meaning. So resistance is impedance. Okay, here is the overall electrochemical processes. Some oxidized species prime in the bulk solution of electrolyte. Sometimes this O prime is chemically converted to O, in this case oxidized species. Then mass transferred into the surface of electrode, then get some electrons from the electrode, then which is reduced into the reduced species. Still those reduced species are on the electrode, then mass transfer out toward the bulk electrolyte, then followed by sometimes chemical reactions. So after removing the chemical reactions, or even with the chemical reactions, we could consider some mass transfer process and also electron transfer, or sometimes charge transfer processes. Anyway, each step has its own kinetics. So kinetics means fast or slow or something like that. So each step can be described by a resistance or impedance. That is to say, the impedance value could be used as a measure of kinetics or rate. For example, a large impedance involved in a process, for example some charge transfer, indicates a slow process of the corresponding process. That is to say, the larger impedance, the slower kinetics, or the smaller impedance, the faster kinetics. Okay, so from these slides I'll try to use the circuit elements for representing our electrochemical processes. Let me start with the Ohm's law. It is the first equation for the circuit element. So, definition of resistance is voltage per current. I have said impedance is resistance, basically. So, impedance Z can be defined by voltage per current. Then let me think about the steady state situation, or let me think about applying some constant potential and current into the system for the resistor, capacitor, and inductor. This situation could be called direct current, or DC, or direct potential situation, which means current is not the function of time and voltage is not the function of time. So steady state. Let me start with the resistor. What kind of impedance can be obtained from the resistor? This is the first equation, Ohm's law. And impedance of resistor was defined by the definition of resistor. So the same thing, V per I, and V per I is equal to R. So impedance of resistor is resistance value, right? So for the resistor, then we could obtain a specific value depending on your voltage and current and measured current. How about capacitor? This equation is about the capacitor potential dynamic equation. Then let me check it. Impedance of capacitor is equal to potential per current, right? And your current is 0 because you didn't move the potential with time. So current is 0, then some value of voltage per current is 0, then the impedance of capacitance is infinity. Because current is 0, current doesn't flow between the two plates of electrodes. So infinity. How about inductor? This is the equation for the inductor, and impedance of inductor is still V per I, and let me say I have applied a constant current into the system. Then this is going to 0, so voltage is 0 with some fixed current. Then therefore the impedance of inductor is going to 0. So we have very simple result. Resistance gives us some value. However, capacitance is going to infinity and inductance is going to 0. So they looks very simple. So I'm not sure we could use those impedance the circuit elements for representing the electrochemical processes in this constant current and constant potential situation. In other words, direct current or direct potential situations. We'd like to get some more amount of information from our electrochemical processes when we are trying to analyze the processes. So let me change the potentials let me change the functions of current and voltage. Let's use the temporal changes of current and voltage, in other words. So in the case, the current function of time would have current function of voltage, or when you apply the time dependent voltage, then you will obtain the time dependent current. So let me change current or potential with time. Any functions could be candidates for function of time for current and voltage. But maybe we'll try to choose the function of time among mathematically well-defined and well-studied functions. Maybe. So for example, how about triangular functions and how about sinusoidal functions? So let me start with the triangular function. You know, what is that? This is the stimuli for the cyclic voltammograms. If y-axis is the voltage and x-axis is the time. So from, for example, 0 volt to 1 volt, then 1 volt to minus 1 volt, then you are going back to the initial potential, 0 volt. Also, you know, in this case, I could say this shape is one period, and then after shortening the period from 2 pi to pi, then you could have 2 cycles within the same time duration. Or when you increase the scan rate like that, and then you have 1, 2, 3, 4 cycles are there. Anyway, I mean, you could use the triangular functions of time for current and potential, and also you could control the scan rate V for changing the period of these periodic functions. However, there is a weak point because this triangular function has the very sharp points. Sometimes at those points we are a little bit difficult to operate some mathematical operations. So let me smooth the sharp point. So it is going to the sinusoidal function. Actually, the sinusoidal function is not coming from the triangular function, but from the viewpoint of shape, it looks similar. So anyway, how about sinusoidal functions like current is equal to initial current 0, actually maximum current, with the sine function of omega t. This is the period, one cycle having period equal to 2 pi. And then if you could increase the frequency or decrease the period, then you could have the 2 cycles in the same time period, and then 4 cycles in the same time period. So angular frequency omega could determine the period of those sinusoidal functions. So let me think about using the sinusoidal functions as the time-dependent stimuli for analyzing the electrochemical processes. Then what happens for the impedance of R and C and L? One more thing, I could say sinusoidal functions are great in terms of convenience for the mathematical operation, because we have the Euler's formula. Sinusoidal functions can be described by exponential functions in complex domain. Look at that. amplitude with exponential function of imaginary unit with phase angle can be described by still amplitude with cosine phi phase angle plus j indicates root minus 1 with sine phi. That is the Euler-Loss formula. So you could convert cosine or sine into exponential functions. Mathematical operations of the exponential function are well known and very convenient. Also, I'd like to emphasize the meaning of a and phi in the complex number domain. So here is the complex number domain. X-axis is the real value and y-axis is the imaginary value. Then let me assume that you have one point here. This point can be described by two things. The first one is phase angle and the second one is the amplitude. So on one point, a single point in the complex plane can be characterized by amplitude with phi phase angle. Here is practice for the Euler's formula. Okay, you have J. This I have said this is the imaginary unit, which is the root square of minus 1. Then can you change this J into the exponential function form? Very simple. J or I is the point here, and then the amplitude of J is just 1, and what is the phase angle? Pi over 2, 90 degree. So amplitude and the phase angle, something like that. So you could use the exponential functions in complex domains when you calculate something in impedance spectroscopy. Okay, so let's use the sinusoidal function of current and potential for obtaining the impedance of capacitors and the inductors. Okay, or sometimes I could say alternative current situation or alternative potential situation. So AC situation. So sometimes impedance spectroscopy is called AC impedance spectroscopy. It means we are using sinusoidal functions. So input could be sometimes potential or current, anything is okay. And let me assume that follows the cosine function with omega t. Then you could convert this cosine function to the exponential function, even if you don't have sine, because every mathematical operation is working in the exponential function term and also cosine function term. So I'd like to use the exponential function instead of cosine function. So for the resistors, let me assume that current is the exponential function of j omega t with the amplitude which is I0. Then what is the potential at this situation? Potential is equal to IR by Ohm's law, and I is here, so this one. Then impedance of resistance or resistor is equal to potential per current, then it is going to just R. So again, impedance of resistor is impedance. It means the current, the amplitude ratio between the current and potential is always the same. Also, there are no phase angle change. So at pi over 2 or 90 degree, you could find the maximum values for current and potential or something like that. So there are no phase change. The phase angle difference is found here. How about capacitors? Let me fix the potential like that as the exponential function. How about the current? Current is obtained by getting the first derivative of the potential. So first derivative, exponential j omega t, and omega t, no, j omega is going out of the exponential function. So j omega with capacitance. And then impedance of capacitor is potential per current. Then this part can be removed and 1 over j omega c. Also, so let me check the this complex number. Let me check the phase angle and the amplitude of this complex function or number. So 1 omega c is not related to j here. So let me get the 1 over omega c as a group, and then still we have 1 over j. So j is this one, exponential pi over 2, but j is on the denominator, so exponential minus pi over 2. It means we have the amplitude like that, and the amplitude depends on where the amplitude is the function of frequency omega, while here w is angular frequency. So amplitude is changing with frequency. Also, phase change is observed, the minus pi over 2 here. What does it mean? Capacitance in the impedance of capacitor, the potential would raise the current. Look at this graph. The potential is going ahead in front of the current. So the difference is pi over 2. So the potential leads the current at pi over 2. That's the meaning. So again, the phase angle change is pi over 2, and the amplitude is 1 over omega c. Let's go to the last element, inductors. Let me fix the current, because in the equation for the inductors we have di dt. Then put it there. Then some j omega is going out of the exponential function. Then finally we could say the impedance of inductor is j omega l. It means also we could convert this complex number into amplitude exponential phase angle. So omega l exponential plus 90 Celsius degree. 90 Celsius degree where pi over 2 means potential will follow the current. With the phase angle difference at pi over 2. So potential is following the current. Plus means minus pi over 2 as the phase change. Minus means plus pi over 2. So potential lead the current. Minus means potential follow the current. Okay, anything is okay. But so here is the summarized. You should memorize the amplitude of impedance of each element plus phase change. How about resistor R and no phase change? And how about capacitor 1 over j omega c and the delta, the phase angle change is plus 90 Celsius degree. How about inductance? Minus 90 Celsius degree, or minus pi over 2. So, two property of each element is very important thing. The first one is absolute value. The other thing is phase angle. Impedance plot is a vector representation in a complex domain. Let me try to describe the impedance as the x and y. That is to say, x plus j or I with y in this Cartesian coordinate. That is to say, the real part of the impedance is on the x-axis and the imaginary part of the impedance is on the y-axis. Then a point has two values, x value and y value. The impedance of resistor is just resistance. We have said about that. That is to say, R plus J with 0. It means you could find the resistance on the x-axis, only on the x-axis. Impedance of capacitor is equal to 1 over J omega C is equal to 0 plus J minus 1 over omega C. So, you could find the impedance of pure capacitor is on the y-axis, and also its value is always negative. So, on this y-axis, you could find capacitor. It should be negative because capacitance value is always positive, and omega, the angular frequency, is always negative, the positive. So the y value of the capacitor should be negative. How about the inductor? Impedance of inductor is j omega inductance is equal to 0 plus j with omega L. So you could find the impedance of inductance or inductor is on the y-axis, which should have positive values. So I could say about this situation like that. Again, x-axis is the real part of impedance and y-axis is the imaginary part. We could locate three different the basis vector. The first basis vector is resistor vector, and this vector is on the x-axis, and the other two vectors are on the y-axis. For the capacitor, you have this basis vector, and here is the inductor vector as the basis vector. So we have totally three basis vectors to describe any plot on the Cartesian coordinate. Usually in electrochemistry, we are using the resistance vector and capacitance vector, not inductance vector. Okay, this I have explained about the impedance in terms of XY representation. Then also we could use A theta representation. A stands for the amplitude, and theta represent the phase angle, or sometimes phi. Actually, I have said about that in the previous slide. The same complex domain in the Cartesian coordinate, and we have a point here. The amplitude is A and its phase angle is theta. So by using A and theta instead of x and y, we could describe any points in the Cartesian coordinate of a complex domain. So Z is A amplitude with exponential of theta j. And how about the resistance? Impedance of resistor is equal to resistance, as you know. So which can be described by amplitude is equal to R and the phase angle is 0. Phase angle 0 indicates we have the plot or point on the x-axis. How about capacitor? 1 over j omega c, as you know, equal to 1 omega c, and the j, the imaginary unit j, can be described by exponential function of minus pi over 2 or minus 90 degree. It means phase angle is minus 92 and the amplitude is depending on the angular frequency. Higher angular frequency, so the amplitude is going to 0, and lower angular frequency, you could have larger amplitude. So that is the capacitance vector, capacitor vector. Then its phase angle is always minus 90 degrees, so you could find the point on the y-axis, actually negative y-axis. How about inductor? Omega L inductance with exponential of pi over 2. J indicates this one, so its phase angle is pi over 2 or 90 degree. So exponential pi over 2. Then, of course, in the same way, you could find the data point on the plus y-axis. So we have, right now you should recognize that we have 3 different basis vector, which are the resistance, capacitor, and inductor vector. By combining those 3 basis vector, you could represent any point in the complex domain. Here is the real experimental, actually simulated impedance data. X-axis is the real part of the impedance, y-axis is the imaginary part of impedance, but in this case usually we have put minus signs because the impedance data of typical electrochemistry is found on this region. So it means plus plus resistor basis and minus y-axis. So usually any point can be described by ZR and ZC. I mean the capacitor basis vector. Usually we want to use the inductance basis vector. Not always, but practically and in most cases capacitor and resistor is enough to describe our electrochemical processes. So usually we have put this minus y-axis upward, so it means the imaginary part should have minus signs. Then you could find very beautiful semicircle here, and the semicircle indicates the Faradaic process. I mean we have a reduction or oxidation reaction there, and we have multiple data points here, and each experimental point is obtained at a single frequency. Therefore we have, for example, 30 data points at 30 different frequencies. Frequency means f or omega. Omega is 2 pi f. Anyway, the frequency direction is coming from here to there. I mean this point, the lowest frequency, and then let me increase the frequency, then we could follow the semicircle on the right position to the left position. At very high frequency, you have a pure resistance. At very low, at very low frequency, you have a pure resistance. Also, at a very high frequency, also you have a pure resistance. The difference between those two resistance is responsible for the charge transfer resistance. You learn about that in the following slides. Between those 2 points, we have a lot of points which have real value and imaginary value. Imaginary value means we have the capacitive element for the data points. So from this electrochemical impedance spectra, we could obtain some information about your electrochemical process, like electric double layer capacitance and charge transfer resistance, and also solution resistance. We will use equivalent circuit models to quantify the parameters to explain your electrochemical processes. Here is the overview about how to use equivalent circuit models for quantification. You would have an electrochemical process, sometimes electrochemical reaction there, sometimes capacitive behaviors are existing on the surface, sometimes mass diffusion or something like that. Then, as the first step, let's measure the impedance by using your frequency analyzer, a machine of frequency analyzer. Then in the experiment, you will change the frequency from high frequencies to low frequencies. Then you would get the multiple data points about the impedance. Each impedance data has real number and imaginary number, or some amplitude and phase angle. Also, each experimental data point is defined at a single frequency. Right now we have the impedance spectra. And then you should set up an equivalent circuit model to which can describe the experimental impedance spectra. By checking the shape, you could set up the equivalent circuit model. For example, here is the ohmic resistance responsible for solution resistance. This could be obtained from around here. You have some resistance at very high frequency. It means we have the solution resistance. Also, this is the semicircle which is responsible for the Faradaic processes. In that case, usually we have set up a parallel circuit of capacitance and resistance. Capacitance is for the double layer, electric double layer formation on the surface of electrode, and the resistance in this parallel circuit is responsible for the charge transfer kinetics. You'll learn about that later. Then, anyway, we'll try to find the values about those three parameters to describe this electrochemical process. Okay, right now we have an experimental data and we have a model to describe the process. Then the third one is data feeding by complex nonlinear least square feeding software. For example, ZView from Scrivener. So by using this software, you will feed like that, and then from this feeding, you would have the value about the ohmic or solution resistance, double layer capacitance, and charge transfer resistance. by comparing those values of each parameter, then you could analyze or characterize your systems. For example, the charge transfer resistance is smaller than that of the other system. It means you have developed a very good and fast kinetics charge carriers or redox active species. Or if you have a very large values of ohmic resistance, the ionic conductivity of your solution is problematic or something like that. So any analysis could be given to you based on the values about parameters of equivalent circuit model. That is the overview of how to use equivalent circuit models to analyze the experimental impedance spectra. Here is the basic models of electrochemical processes, which is based on ideal circuit elements like resistance and capacitances. The first one is non-faradaic process systems, that is to say, electric double layer formation on the surface of electrode. This process can be described by the solution resistance plus double layer capacitance in series. Let me go to inside of electrolyte. When you have applied some negative potential into electrode, then the positive ions in bulk electrolyte is moving toward the surface of electrode. This process, the ionic conduction movement, can be represented by solution resistance or electrolyte resistance. If you have higher values of Rs, then it means your electrolyte is not very conductive in terms of ionic movement. Or if you have low solution resistance, it means your electrolyte is well conductive in terms of ionic movement. Then, after these plus ions reach the surface of electrode, then the electric double layer is formed on the surface of electrode, plus and minus. Or if you have applied some positive potential into electrode, then minus ions and plus charged surface. So this phenomena can be described by capacitance, so-called double layer capacitance. So these overall non-faradaic processes could be represented by the series circuit of solution resistance plus double layer capacitance. The overall impedance is solution resistance plus impedance of capacitor. This is serial connection between those two elements. So the resistance is just a simple summation of those two impedance. Then Rs minus J per omega C dl. Here is the complex plane. X-axis is the real, y-axis is the minus imaginary. So when you change the frequencies from low frequency to higher frequency, then the impedance follows the vertical line from the top to the x-axis. The point on the x-axis indicates solution resistance. Also, the frequency dependence vertical line indicates some capacitance. That is the simple non-faradaic processes. This is very ideal case. In the practical capacitive processes or non-faradaic processes, you would have some line with some phase angle. Right now this vertical line has the phase angle at 90 degree or pi over 2. However, in most practical situations, this line is a little bit inclined toward the x-axis onto the right side. So like that. Frequency low to high. So usually at high frequencies, at very high frequencies, you could find the solution resistance in any cases, even for the Faradaic reactions. Let's go to the second situation for the Bayesian models. That is the so-called Landry circuit, which simulate the Faradaic reactions. When you apply the negative potential for making some reduction, at the very first time, the positive ions is moving toward the surface of electrode, which is the same situation in the non-Faradaic processes. Of course, we could involve the solution resistance in the equivalent circuit model. And then finally, the positive ions are on the surface of electrode, and then at this time we have two simultaneous events there. The first one is electric double layer formation, like in non-Faradaic processes. So here is the capacitance of double layer. One more thing. The cations on the surface would get some electrons from the electrode. Then these plus ions is reduced into the reduced species. So those two events, including electric double layer formation and charge transfer process, happens at the same time. So the resistance responsible for the charge transfer should be connected to the capacitance of double layer in parallel. So current is flowing two ways. One is going to the capacitance and the other is going to the resistance. This is so-called Landry circuit, and which is responsible for the Faradaic reactions. Total impedance is the sum of solution resistance plus impedance of the parallel circuit of R and C. So let me say Z, R and C with parallel. Also, this the impedance of parallel circuit of RC can be obtained by reciprocal summation of those two components. That is to say, 1 over impedance of this circuit is equal to 1 over impedance of capacitor. So the impedance of capacitor is 1 over j omega CDL. So its reciprocal term is going to j omega C double layer plus 1 over RCT. By combining those two equations, you have the semicircle on the impedance plane or complex plane. This complex plane is sometimes called Nyquist plot. Let me write down the Nyquist plot here. Nyquist, N-I-Q, Nyquist, U-I-S-T. Oops, Nyquist plot. So this is the Nyquist plot, and for the Faradaic processes, practically you have this kind of semicircle. By combining those two equations, you could obtain the equations for circles. So here is some formulation, and finally you would have real part minus r over 2 square plus imaginary square is equal to r over 2 square. It means here r stands for RCT. Therefore, the resistance of charge transfer is diameter of the semicircle. So you could easily estimate the value of charge transfer resistance from this Nyquist plot. So let me explain about this Landers circuit in a more detailed way in the following slide. Let me read the Faradaic reactions from the viewpoint of the circuit element. Why we should have the solution resistance and also the sum of solution resistance plus polarization or charge transfer resistance on the x-axis. At frequency increases, that is to say omega or 2 pi f is going to infinity, then the impedance of capacitance decreases into zero. So impedance of capacitor for the double layer is going to zero. Look at that. Impedance of capacitance is 1 over j omega CDL, and omega is going up, then the impedance of capacitor is going down. So finally, this line looks like a conductor, like just copper wire. So electron flow prefers the double layer formation pathway this way rather than the charge transfer pathway, not this way, in the parallel circuit. So current flows through RS, then just copper wire, then going to the other way. Therefore, the overall capacitance is Rs in this case at extremely high frequency. So this point is obtained at high frequencies. Finally, we could obtain the solution resistance. Let's go to the other extreme case. As frequency decreases, that is to say omega is going to zero while frequency f is going to zero, the impedance of double layer capacitance increases. That is to say, the value of impedance, this part is going up to infinity. Then the electrons don't like this pathway. Electron flow prefers the charge transfer pathway in this way. So like following this yellow line. Therefore, the overall capacitance is Rs plus R charge transfer at extremely low frequencies. So we could find the Rs plus R charge transfer on the right side on the x-axis at low frequencies if you have a pure Faradaic processes without any diffusion there. Okay, the same thing. And low frequency, then the frequency increases along this semicircle, and then finally we have met the x-axis again at very high frequencies. At high frequencies, you could obtain the value about the solution resistance in the same way shown in the non-Faradaic processes. Also, I have said the diameter of this semicircle is the solution, the polarization resistance or charge transfer resistance. This one. Okay, this one, Rs, and the diameter is charge transfer resistance. And then how could we obtain the values of capacitance by your hands? Please check the angular frequency at the maximum value of imaginary part. So this part, this point, looks like the top point of the semicircle. So omega at G prime maximum is, let me say, omega max G prime is equal to 1 over RC. R stands for charge transfer resistance, and C stands for double layer, the capacitance. And also, this is the angular frequency. Sometimes angular frequency can be converted to the just frequency, 2 pi frequency at the maximum point or top point of the semicircle. Then you would estimate the RCT value from the diameter. Then also after you measuring the omega at the top point, then you could calculate the double layer capacitance. It's very simple. Of course, it is not the exact way to evaluate the values of each parameters, RS, CDR, and R charge transfer. However, those values would be the first guess for the exact fitting of experimental data. You should use some software. I have said about that in the previous slide, based on the complex nonlinear least square fitting. However, you could guess the values by your eyes and by simple calculation, RS, RCT, and then capacitance of double layer. I have said about the Bayesian models. Bayesian models means the models have very ideal circuit elements like resistance and also capacitance. However, sometimes we could not express the behavior of impedance by the Bayesian models. I'd like to give you two more elements, which is called non-ideal or distributed elements. The first one is Warburg element. Warburg element is responsible for diffusion process. Impedance of Warburg is equal to sigma with j omega to the minus 0.5. Let me guess what kind of the curves are obtained from these equations. Impedance of Warburg is equal to sigma j omega to the minus 0.5. Just I have copied this one. And then sigma omega to the minus 0.5 is root omega. Then j to the minus 0.5. What is the j? This j can be expressed by exponential function, like the amplitude is 1 and the phase angle is pi over 2. That is the j. So exponential pi over 2j. Then exponential this one to the minus 0.5, like that. Then minus 0.5 is going into the exponential function. So exponential minus pi over 4j. It means the phase angle of this impedance would have minus pi over 4, like 45 degree. So then let me convert this A theta representation into the xy representation by using Euler's equation, Euler's formula. Then 1 over root 2 1 minus j. So the final equation like that. Usually in the complex domain for impedance, or sometimes called Nyquist plot, we are using the negative y-axis. So in that case, we have the phase angle at 45 degree instead of minus 45 degree. So 1 minus j. This vector is following or along this green line. So Warburg impedance gives us the 45 degree lines. Let me summarize it. For the non-faradaic process or capacitive process, we have vertical line, the phase angle of which is pi over 2, actually minus pi over 2. That is for the capacitive behavior. However, when the line is inclined into the 45 degree, actually minus 45 degree, then that line is responsible for the process of diffusion. So we have a difference between capacitive charging and diffusion process by using the phase angle. That is the Warburg impedance. Again, sigma j omega 2d minus 0.5. Then here is the fourth circuit element, which is a non-ideal one. That is called constant phase element, or CPE. The CPE is the extension of Warburg impedance and also the capacitor impedance. It looks like that. Impedance of CPE, Q represents for CPE. Impedance of CPE is equal to some amplitude with j omega minus n, 2d minus n. The shape of function is very similar to the Warburg impedance, excluding the exponent. In this impedance, we have used the one more parameter like n. If n is going to 0.5, what is that? The CPE is going to Warburg. When the n value is going to 1, then 1 over j omega. What is that? That is the capacitance. Usually, CPE has the exponent value between 0.5 and 1.0. Again, the 1.0 indicates the capacitance, 0.5 indicates the Warburg. Usually between them, we could obtain some values of CPE impedance. Let me try to plot it. So in the same way, I'd like to start with the equation about the impedance of CPE, like that, j omega minus n value. So following there, then finally you have this kind of things. So in front of j in the exponential function, we have minus pi over 2n. It means its phase angle is pi over 2 by n. It means 90 degree by n, and n is between 0.5 and 1.0. n is equal to 1. This line is vertical line. That is to say, that is the capacitor. However, n is going to 0.5. The phase angle is 45 Celsius degree. It means Warburg impedance. Practically, it is very difficult to find exact Warburg impedance and exact capacitance impedance. The phase angle is not like 45 degree or not like 90 degree. So usually practical number is 88 degree and 47 degree or something like that. So usually we are using the CPE, constant phase element, instead of Warburg and instead of capacitance in the simulation program. So what you should know for the circuit elements used in the complex nonlinearist square fitting programs, you have only two things. The first one, resistance. The second one, the constant phase element, CPE. Please memorize those two things, resistance and CPE. let me extend the Landers circuit to the diffusion process with Faraday reactions. In the previous slides, I have said about the Landers circuit, which have solution resistance with a parallel circuit of double layer formation and charge transfer process. But actually it is not true. This one is not the Landers circuit. Actually, the classical and true Landers circuit have diffusion process. So here you could find the Warburg impedance with the charge transfer process. I'd like to read this circuit again. Electroactive species in bulk electrolyte is moving toward the electrode, so experiencing some solution resistance. Then on the surface of electrode, we have two pathways. The first one is capacitance pathway and for the double layer formation, and the second one is charge transfer process. In the charge transfer process, I'd like to introduce the mass transfer process based on the diffusion process. That is the Warburg impedance. So we have two components here for the charge transfer pathway. That is the original Landers circuit. Let me think about the situation of the alternating potential stimulation onto the electrode. Here is the electrode and here is the electrolyte. We have an electroactive species pair, which is Fe3 plus and Fe2 plus. Then I'd like to apply a potential at plus 0.76 volt versus normal hydrogen electrode, the value of which is the standard reduction potential of Fe3 plus 2 plus pair. So on the surface, we would have the equimolar concentration of Fe3 plus and Fe2 plus, maybe 5 minutes after we have applied the potential at plus 0.76 to this system. So right now on the surface, we have Fe3 plus and Fe2 plus at plus 0.76 volt. Then let me introduce some small amplitude alternating signal. The maximum value is minus 10 millivolt and the other maximum value is 10 millivolt. That is the sinusoidal function applied on the biased potential at plus 0.76 volt. It means, again, minus 10 millivolt indicates plus 0.759 volt, because minus 10 millivolt variation is applied into this biased potential. Plus 10 millivolt indicates plus 0.761 volt. So we are going to the negative and then positive around the plus 0.76 volt. We are investigating the electrochemical process at plus 0.76 volt right now. So at minus 10 millivolt variation, Fe3 plus is reduced into Fe2 plus. Or at plus 10 millivolt, Fe2 plus is going to oxidize into Fe3 plus. The kinetics of charge transfer between Fe2 plus and Fe3 plus is really fast. So the oxidation or reduction follows any frequencies of the plus minus 10 millivolt variation. Even at very high frequency, minus 10 millivolt, and then immediately is going to the plus 10 millivolt in the sinusoidal function. But Fe3 plus reduction and Fe2 plus oxidation would follow the speed of the change of this potential, because the charge transfer kinetics is really fast. However, let me think about the diffusion process or mass transfer process. At minus 10 millivolt, Fe3 plus is converted to Fe2 plus. So we would experience the lag of Fe3 plus. So Fe3 plus is diffused from the bulk electrolyte into the surface, or vice versa. But the speed of the Fe3 plus or Fe2 plus diffusion is really slow. So let me think about the situation at very fast alternation of plus 10 millivolt and minus 10 millivolt. Okay, so we are going to the minus 10 millivolt plus 0.76 volt. Then Fe3 plus is trying to go to the surface of electrode to provide more amount of Fe3 plus into the electrode. However, I have said the movement is very slow. So before the movement, I'd like to change the minus 10 millivolt variation into the plus 10 millivolt variation along the sinusoidal function. Then, at this time, Fe3 plus is trying to go away from the electrode surface. But also, at this time, before this movement, also I'm back to the minus 10 millivolt. Then again, Fe3 plus is trying to go toward the electrode. That is to say, at very fast alternation of potential from minus 10 millivolt to plus 10 millivolt or vice versa, then Fe3 plus cannot move toward or out of the electrode at such a very fast frequencies. Of course, if you are using the very slow the change of the potential, then Fe3 plus could move toward or out of the surface. So I mean, at very low, at very high frequency alternation of the small amplitude of potential around the plus 0.76 volt, only we could detect only the electrochemical process of charge transfer. We cannot detect the mass transfer in this case. However, at low frequency of alternation of the small amplitude around the biased potential, then we could detect the charge transfer process, of course, and then plus very slow mass transfer process could be detected at such low frequencies. So let me read some statement here. We popularly meet mass transfer limited systems where kinetic capability of charge transfer is faster than that of mass transfer. Fe3 plus, Fe2 plus is that case. At high frequencies, only the faster charge transfer is detected, this one, because the diffusion of electroactive species cannot follow the speed of alternating potential. The Fe3 plus cannot move toward or out of the surface. So, at high frequency regions, you could find just pure Faradaic process looking like the semicircle, not the impedance here is the reason. So at this high frequency region, we could say the impedance can be controlled by the kinetics of charge transfer. And then let's go to the low frequency region. At low frequencies, all processes involving diffusion as well as charge transfer are detected. However, this is important thing. However, the capacitance component of charge transfer approaches zero at frequencies. So, I have said, at high frequency region, we could find everything. Charge transfer, mass transfer, But you should think one more things. At low frequencies, the capacitance value is going up. So the electron flows through the second pathway of charge transfer, not through the capacitance pathway. So RCT means the X component of Nyquist plot. So we don't need to think about the capacitance value. It means y-axis value. Again, I'd like to read again. However, the capacitance component means the y-axis value. The capacitance component of charge transfer approaches zero at low frequencies. So look at that. Let me follow the semicircle line. Some values of capacitance, y-axis means capacitance. Some values of capacitance is going down, and then finally it is going to zero. So therefore, we could easily decouple the charge and mass transfer regions by frequencies. So at this region, we would find the charge transfer plus mass transfer. But fortunately, we don't need to think about the effect of the charge transfer process on the mass transfer process, because the imaginary component or capacitive component of charge transfer process is going down to zero at this low frequency region. So at the low frequency regions, you could distinguish the mass transfer thing from the charge transfer process. Therefore, we could easily decouple the charge and mass transfer regions by frequencies. So at low frequencies, at high frequencies, charge transfer. At low frequencies, mass transfer. In the previous slides, you have learned about how to estimate the values of parameters, including solution resistance, from the x-axis at the very high frequencies, and then charge transfer resistance, which is the diameter of the semicircle, and capacitance, double layer capacitance values from the top of the angular frequency. We could calculate the CDL. In this equivalent circuit model, we have one more thing, Warburg impedance. So I'd like to give you how to estimate the parameter of Warburg impedance. I have got this formulation from the previous slide, and Warburg impedance is defined by sigma, that is the parameter, with j omega 2d minus 0.5. Here we have a single parameter, sigma. Then when we convert this impedance into the x plus jy representation, then we could say sigma per root 2 omega with 1 minus j. Then by using these equations, I'd like to calculate the value of sigma. Let's go back to the Nyquist plot of the Landau circuit. So semicircle, and then at low frequencies, you could have the Warburg impedance. I'd like to use the end of the data at very low frequencies, because at low frequencies, the imaginary parts of Warburg impedance are not affected by the impedance of charge transfer process. So at this region, charge transfer resistance or impedance is going to the zero. So at very low frequencies, only you could find the mass transfer in terms of the imaginary part of impedance. So imaginary part of impedance of Warburg is sigma over root 2 omega. Right? Actually minus sign, but I'm thinking about the absolute value of the imaginary part. So sigma per root 2 omega. And then In GView, which is the software to fit the experimental data with the equivalent circuit model, sigma is defined by 1 over t. So in this equation, I'd like to use 1 over t instead of sigma. So imaginary part of Warburg impedance is equal to 1 over t and 1 over root 2 omega. I'd like to calculate the value about t. T is a kind of capacitance. Then let me say at 0.001 Hertz, we have 28 ohm on the x-axis and minus 9 ohm on the y-axis. So let me put those values into the equations. Imaginary part 9 is equal to 1 over t, and then 1 over 2 omega. What is the omega? Omega is 2 pi with frequency in hertz. So 0.001 hertz by 2 pi. Then you could calculate the value of t. In this case, t is equal to 1. So we could calculate the parameter for Warburg impedance. I'd like to present the real electrochemical impedance spectra for some applications. Here we have two examples. The first one is from the batteries, lithium-ion batteries, and the second one is dye-sensitized solar cells. Let me start with lithium-ion rechargeable batteries. This is the anode for the lithium-ion batteries. This is copper plate, which could be used as the current collector or electrode. On the copper current collector, we have two things. Graphite is the active materials to which lithium ion is intercalated during Faraday reactions. The other thing is carbon black. Carbon black provides an electric conduction pathway from current collector to the graphite. Lithium ion is intercalated into the graphite when you have applied a negative potential into current collector. These electrons are conducted through the carbon black and then finally reach graphite. At the same time, lithium ion is intercalated. One more thing. Around the graphite particles, we have a passive film, so-called solid electrolyte interface layer, shortly SEI layer. That is the situation. And how many circles can you expect from this system? Let me think about the viewpoint of lithium plus. Lithium plus is transported through the electrolyte. So we have the solution resistance here. And then the first interface lithium ion should transfer is electrolyte and SEI layer interface. So lithium ion is jumped into the SEI layer with the help of electron. So the first circle is related to the electron transfer, while charge transfer through the interface between electrolyte and SEI layer. That is the first semicircle, and this first semicircle can be described by RC in parallel. C for the capacitance of SEI and resistance for the charge transfer through the interface. And then let's go to the second semicircle. Right now we have lithium ions inside of SEI layer, and then the second interface lithium plus ions are meeting is the interface between SEI and graphite. So the charge transfer through the interface between SEI and graphite would make the second semicircle. Of course, charge transfer resistance and double layer formation. Then lithium ion would travel inside of the graphite. So this is a kind of diffusion, actually solid diffusion, more accurately solid diffusion. So we should have Warburg impedance here. So the second equivalent circuit model is the Landry circuit. So by using those three parts, we could describe the system of lithium-ion batteries when lithium ion is intercalated into graphite. That is the first example. Let's go to the second example, dye-sensitized solar cell. This is the solar cell. Let me explain the principle, working principle of the SSC, dye-sensitized solar cell. Here is the conducting glass, because we need to use the solar ray. So the solar ray are introduced into the system through the conducting glass. And on the conducting glass, we have titanium oxide. And on the surface of titanium oxide particles, we have some dye, photosensitized dye. When the light is incident into the dye and the electrons of dye is excited from the ground state to the excited state. Then the electron is transferred to titanium oxide, then conducting glass, then through the copper wire, then finally reach the counter electrode, usually which is the platinum. And platinum is donating some electrons into the electroactive species inside of electrolyte. This electroactive species is called mediator in this system. So oxidized mediator is reduced into reduced mediator after getting the electron from the platinum electrode. Then this guy is dumping their own electron into the empty ground state. So again, this electron is excited by solar ray and then going through the titanium oxide, conducting glass, copper wire, finally going to the counter electrode. That is the working process, dye-sensitized solar cell. That is to say, by using solar rays, we are making the electron flows continuously. How many semicircles are there involved in this system? 3 or 4 or something like that. So here is the experimental data, and just follow the field square spectra like that. And we have first semicircle, second and third semicircle. Let me assign some equivalent circuit, actually RC parallel circuit, into each semicircle. The first one is the electron transfer between titanium oxide and conducting glass, so-called FTO. So we have R and C, capacitance, resistance, and capacitance in parallel for describing the semicircle. In this case, instead of capacitance, we have used the CPE. I have said, please try to use the CPE instead of capacitance when you are using the software for feeding experimental data with equivalent circuit model. But in your by hand calculation, capacitance enough. Then let's go to the second circle. What is that? What is the cause for making this semicircle. This semicircle is expected from the electron transfer between the mediator and dye or titanium oxide. Anything is okay. So in this case, electron is coming from the reduced species of mediator to the empty ground level of dye. So we have Cp for trying to describe the capacitance, and then the other thing is recombination or the recombination resistance. This is about the electron transfer. Actually, back transfer of electron from the ground state into the oxidized species of mediator. But don't try to understand the exact meaning of each compartment. Just I'd like to give you an example for the electrochemical impedance spectra. The other thing is Warburg, and this Warburg is related to the electron transport through the titanium oxide. So anyway, the semicircle is responsible for this electron transfer, then the electron transport through titanium oxide. The other thing, the Warburg for the mediator transport through electrolyte. But in this case, you couldn't neglect in the experimental data. The third semicircle is relevant to the charge transfer or electron transfer between platinum to mediator. So we have the charge transfer resistance and also capacitance or Cp. So by using 3 RC parallel circuits, we could describe the electrochemical impedance spectra of dye-sensitized solar cells. That's it for chapter 6 about the electrochemical impedance spectroscopy, or shortly EIS. That's it.